So in this video, we're going to talk about inverse trig functions. And the first thing we want to remember is that for a function to have an inverse, it has to be a one-to-one function. So if we were to just look at the sine function, so remember it goes this way forever and this way forever. And that's not the greatest. Let me see if I can get it better. There we go. That's a little better looking. So the sine function y equals sine x is not a one-to-one function. And because it's not one-to-one, that means the whole entire sine function does not have an inverse. But what we actually do is we can restrict the sine function. So we can restrict it between these two values here. And these happen to be minus pi over 2 and pi over 2. And so because we restrict it that way, we can say on that little tiny bit, the sine function does have an inverse. And so because of that, we have to actually tweak domains and ranges when we are dealing with inverse functions. So the first thing I'm going to do is kind of write down, show you the inverse functions and show you the restrictions of the domains and ranges. So the first one we're going to look at is y equals the sine inverse of x. Now some books, or once in a while on Alex, you might see this written as the arc sine of x. So this inverse is really an abuse of notation because we're used to this -1 being like a power, and this is the same as 1 over sine x, but in our case it's not. So I'm just going to write a little note over here. Sine inverse of x, it is not equal to 1 over the sine of x. So it is the notation we're using to say that there's an inverse. And so the way that the graph looks is like this. It goes between -1 and 1, and it's as high here as pi over 2 and as low as minus pi over 2. So the domain is -1 to 1. The range is minus pi over 2 to pi over 2. And what that means is when we're dealing with that, we're dealing with angles that are in quadrant 1 or also quadrant 4. But I'm going to put a little star next to quadrant 4. Anytime we deal with stuff in quadrant 4 with inverse functions, we're going to have to be a little careful. And so I'll come back and tell you why we're going to be careful in a minute. We can also look at y equals the inverse cosine of x. And again, that's not 1 over the cosine. You could also write it as arc cosine. Arc cosine x. And so here, this function looks like this, and it's going between, again, -1 and 1, but this time it's going all the way up here to pi. So the domain is -1 to 1, the range is 0 to pi, and it is in quadrants 1 and 2. And these are just coming from where we're restricting things. So the last one I'm going to draw is y is the inverse tangent of x, or the arctan of x. And this function actually looks like this. So remember, when you're trying to find inverse functions, you're swapping the x and y, or you're reflecting the graph over the line y equals x. So that's how I'm getting these. And so this is minus pi over 2 to pi over 2. And the domain here is from -infinity to infinity. The range is from minus pi over 2 to pi over 2. So again, we're in quadrants 1 and 4, but I'm going to put that little star. So the little star means when in quadrant 4, we must write the angle as a negative. angle. And in a minute here, I'm going to do some examples to show you what that means. Before I do that, I just want to write down what the domain and range is for y equals the inverse cosecant of x. We're not going to draw these graphs, but the domain on that is from minus infinity to minus 1, union 1 to infinity, and the range is minus pi over 2 to 0, union 0 to pi over 2. So again, we're talking about quadrants 1 and 4. So again, little star there. Y equals the inverse secant of x. The domain is minus infinity to minus 1, union 1 to infinity. And the range is 0 to pi over 2, union pi over 2 to pi. So this is quadrants 1 and 2. And then, actually if I erase this, I can put the last one right here. Y equals the inverse cotangent of x. And the domain is minus infinity to infinity. And the range is 0 to pi. So it's also quadrants 1 and 2. Okay, so the most important thing to remember is the quadrants. So I'm going to write them down here. So y equals inverse sine of x. We're talking about quadrants 1 and 4 with that star. Y equals the inverse cosine of x. We're talking about quadrants 1 and 2. Y equals the inverse tangent of x. We're talking about quadrants 1 and 4. Y equals the inverse cosecant of x. We're talking about quadrants 1 and 4. Y equals the inverse secant of x. We're talking about quadrants 1 and 2. And finally, y equals the inverse cotangent of x. Again, we're talking about quadrants 1 and 2. Okay, so for example, find the exact value of a cosine inverse of 1/2. Okay, so I always think when you're working with the inverse functions, it's much easier to think in terms of the in terms of the regular trig functions, not the inverse functions. So what I do is I always set these equal to theta. Some angle, this inverse cosine is going to be equal to some angle. And I can rewrite this now to say that the cosine of theta is equal to 1/2. And so remember, cosine represents the x value on the unit circle. So we want to go to the unit circle and we want to think about when is the cosine equal to 1/2. And that happens when theta, and remember, because here the cosine, we're only worried about quadrants 1 and 2, it happens in quadrant 1, and it happens to happen in quadrant 1 when theta equals pi over 3. So the general thing is, my steps are rewrite as trig without the inverse. Then look up what quadrants to look in. Then find the value on the unit circle. And if we do one that's in quadrant 4, we're going to have to tweak it a little bit, which I have some examples we'll do here in a minute. So here's another one, inverse sine of 0. So again, I'm going to set that equal to some value theta. I'm going to rewrite. So we're saying that the sine of theta equals 0. So if we think about when is the sine of theta equal to 0, well, that happens when theta equals 0. So my answer here is 0, just like my answer here was pi over 3. So we'll do another one. The inverse sine of minus root 2 over 2. So the inverse sine of minus root 2 over 2. So again, I'm going to think of it as that's equal to some angle. So we're really saying the sine of an angle equals minus root 2 over 2. So if you go onto the unit circle and you find where the sine is equal to minus root 2 over 2, remember, because we're dealing with the sine, we're only looking in quadrants 1 and 4. So if I look in quadrants 1 and 4, it is equal to minus root 2 over 2 at the angle that comes down here. So this angle here, and if you look up what that is, it's 3 pi over 4. But rather than swing that direction I just did to get to the angle, what we want to do is we want to swing counterclockwise. So swinging 3 pi over 4 all the way is the same instead as going negative pi over 4 in the direction. So the answer here is minus pi over 4. And this works for all of these different problems. So for example, if you're looking for the inverse tangent of negative 1 being equal to, or inverse tangent of negative 1. So again, I'm going to set that equal to theta. So we're looking for the tangent of theta being equal to negative 1. So again, I need to look in the fourth quadrant because my tangent is, we're worried about quadrants 1 and 4. I'm looking in the fourth quadrant. The tangent is equal to negative 1 at 3 pi, not 3 pi, sorry, 7 pi over 4. Oops. At 7 pi over 4. And so we want to go down this way, and so that's going to happen. We're going minus pi over 4. So this is another one that's minus pi over 4. And again, if I go back here, I wrote the wrong thing. This should have been 7 pi over 4, not 3 pi over 4. Sorry about that. Okay, so I have one more example for us here. So if we're looking for the inverse secant of root 2. So again, the inverse secant, we're going to say that's equal to theta. So we're looking for when is the secant of theta equal to root 2. And I think it's kind of hard to think about secants. So instead I'm going to change it to, if the secant is equal to root 2, that means the cosine is equal to 1 over root 2. And 1 over root 2, so remember, if I were to rationalize this, this would end up being root 2 over 2. And so that happens when we're in cosine, so we're looking in quadrants 1 and 2. And that happens when theta actually equals pi over 4 in quadrant 1. So the thing about inverse trig functions is really to understand that when you're doing inverse trig functions, you're really talking about just finding an angle that gives you that value.